Alright, welcome to what will potentially be a new video series on, as you can see over here, it's an intro to proofs and logic. And this kind of stuff doesn't get taught a lot, but in my opinion, it's very useful actually. There are lots of ways that you can apply proof and logic, but the way we're going to do it is through a mathematical viewpoint. And I think that it's going to be easier to understand with a mathematical viewpoint than through the other options that are available. And yeah, so without further ado, let's just begin with a little introduction here. So basically, a lot of things in maths has to do with patterns. So that's how we're going to introduce the idea of proof and logic. And that is through analyzing a specific pattern, which I'm going to show right now. So let's say you're some mathematician from the ancient times, right? And you came across a pattern, which I'm going to show you comes in the form of a table. So let's just draw a table right here. And on one column, we're going to have n, and that's just a variable that can stand for any number whatsoever. And on the right column, we're going to have 2 to the power of n minus 1. So how are we going to construct this table? Well, we have to fill in random values for n over here. And the easiest way we're going to do that is just basically going from 1 to 5. That's the easiest way to do that, and it also fits with the size of the table here. So what's going to be in the right-hand column then? Well, that's just 2 to the power of whatever's here minus by 1. So 2 to the power of 1 minus 1 is just 1. And 2 to the power of 2 minus 1 is 4 minus 1, which is 3. 2 to the power of 3 is 8. 8 minus 1 is 7. 2 to the power of 4 is 16. 16 minus 1 is 15. And 2 to the power of 5 is 32. 32 minus 1 is 31. Now you might be asking, like, where's the pattern? This doesn't seem too interesting. Well, the pattern actually comes when we ask which one of these numbers here are prime and not prime. So let's add another column over here. That's just going to be P question mark, I guess, to show if whether or not the numbers are prime or not. So 1 is not a prime number by convention. So this is, both of them are not prime numbers. 2 is a prime number. 3 is also a prime number. 3 is a prime number. 7 is a prime number. And I think you know where this is going. 4 is not prime because it's divisible by 2. 15 is not prime because it's divisible by 5. 5 is a prime number, and 31 is a prime number too. So you can see the pattern right now, right? And based on this pattern here, when one column is no, the other column is also no, and when one column is yes, the other column should also be yes. You are gonna right now form two theorems. Alright, so now that we have this pattern, let's formulate our results, right? We want to turn these into theorems that you can just publicize and show to the world. So what can you base off of this pattern? Well, when n is prime, 2 to the power of n minus 1 is also prime. Right, so that's your first theorem or first statement. And the second one is, if n is not prime, 2 to the power of n minus 1, also not prime. And these are your two theorems, two statements, whatever you want to call it. And I did not select everything entirely, but that's fine. Let's just redraw it again. Alright, so these are your two theorems. Now, the problem is Do you think that the table is enough justification? Does it provide enough evidence to say that these two theorems exist? And can you give an argument as to why you think it works or why you think it doesn't work? And basically that's it. That's what proof and logic is about. Why do things work and why do things not work? So let's analyze this question a bit more, right? So let's just draw it over here. So is the table good? And if there are other methods as well, are they better? And what exactly about these other methods that make them better than the table? And that's what we're trying to answer here. So let's pay attention to the table first, right? Because that's what we have right now. Well, obviously, I think we can make this table better, right? I mean, if we have a bigger table, it might work as a better evidence, right? If we have a table that has 100 entries or maybe even 1,000 entries, and like all of this pattern still holds, then maybe that's a better evidence, right? So let's say we hypothetically expand this table out till some really big number, I don't know, like about 1,000 or something. Then is it good enough as a piece of evidence? And if it's not good enough, then what if we make it till the millions or billions? Will that be better? Or if that's still not good enough, can we just keep going on? The real answer to that is the table is never going to be good enough, no matter how big it is. And let's just try to give an argument as to why the table is not good. Alright, so let's just get rid of this for a while. Alright, so what can the table show us exactly? It can show us individual examples here. Like this is one example when n equals to 5. And likewise, other entries as well, they are also examples of the theorem working out. And if you expand this table, then that would mean that you would have 100 or 1,000 examples of the theorem working. But what the table can also show you is a counterexample. Maybe they exist out there, you know? What if this pattern doesn't hold? What if it doesn't work for some certain number? That could be seen from the table too, right? And in fact, a counterexample does exist in this table. It exists when n equals 11. And 11 is prime, but it turns out that 2 to the power of 11 minus 1 is not prime. Now this is what we call a counterexample. Well, it's just exactly the opposite of what an example is. An example is just, well, it's an example of the theorem in action, while the counterexample over here is the theorem basically not working. And 2 to the power of 11 minus 1, if you use a calculator or something, you're going to get, hold on for a minute, I need to search that number up. You're going to get 2047. And this is not prime because it can break down into 23 times 89. But that's not really important. The fact is that counterexamples exist and we can find them with our table, if our table is big enough. So what does a counterexample tell us? Does having a counterexample mean that the theorem is false? Well, if we think about it, yeah, I guess this statement is true. Why? Because, well, look at what this statement is talking about. If n is prime, then 2n minus 1 is also prime. But this turns out to be a blatant lie. Why? Because 11 is prime, right? But 2 to the power of 11 is not prime. So this statement just turns out to be a blatant lie. And we can safely say that this statement is false. And let's just give it an X mark right there. So, okay, good. We eliminated one possibility. What about the other one here? Well, maybe we can find a counterexample as well, right? We just have to make the table big enough. The thing is, no matter how big your table is, I'm just gonna spill the secret out. This pattern will always hold. If one column has an X in it, the right column should have an X as well. And this pattern holds even for tables which are infinitely large, let's just say. Now, what exactly does that tell us, right? Does it mean that this theorem is true? In other words, we're going to ask the question, if there is no counterexample, does that mean that the theorem is true? So you can see that this is basically a modification of this statement over here. Alright, so what do you guys think? Is this statement true? I mean, the statement at the top is certainly true, but the bottom one is, I guess you can say it's a bit less clear. So we're gonna have to argue our way out of this one, right? The answer is this statement over here is false. And let's try to understand why that is so. So when we say that there's no counterexample, that means we can't find one on this table over here, on this infinitely sized table. So basically any number n, if we put it into the table, it can either become an example or it can be a counterexample if we put it in the table. So if n equals to 1, n is an example of the theorem working. Then if n equals to 11, then that is a counterexample. So any value of n can be separated into either an example or a counterexample. So let's think of n as an infinitely sized bucket, let's just say, right? So infinitely sized bucket with many balls inside of it, and each ball corresponds to a number. And this is infinitely sized because we have infinitely many numbers, right? That's obvious. So each ball represents a number, and each number can be either an example or a counterexample. So basically when we're making the table, what we're doing is we're picking a ball from this infinitely sized bucket, and we're checking to see if it's an example or a counterexample. Yeah, let's label the examples with green and counterexamples with red. So if I can just... Alright, so some of these balls are red and some of them are green, like so. And I'm not gonna color every single one of them because that's gonna take a lot of time. But you get what I'm talking about. Just imagine that the rest of them have colors or something. So let's say we pick a ball from this huge bucket, right? And it turns out to be green. And I'm too lazy to select the color from the option menu there, so just imagine that it's green here. And we pick another ball and it's green. Okay, all right. And let's pick another ball again, and okay, that turns out to be green as well. Pick another ball, and that turns out to be green, and it happens so on and so forth. So there are no counterexamples, we can't find any of them, and all that we're getting is examples. Does that mean that every ball in this bucket is green? Well, no, you can't make that argument. And remember, this is an infinitely sized bucket, right? So no matter how many balls you take, maybe there still could be a red one inside, and you're just never gonna know. And it doesn't matter how many balls you pick, because this is a never-ending bucket. You're never gonna know if there is a red one inside or not, because you can't empty the bucket. And it doesn't matter if you keep getting green balls every single time. That statement has no relationship with whatever's in the bucket or not. So returning over here, we can say that this statement here is false. That means we can't use this statement to say that theorem number 2 over here is correct. We can't, because we can't use this statement. We can't use this argument. It's not valid because we have an infinitely sized bucket over here. And we can't say anything about an infinitely sized bucket by taking things out of it one by one. It's just not a valid argument. So we're apparently stuck. We still don't know if this theorem is true or not. We don't have a valid argument. So we're stuck. We're stuck, okay? We don't know whether this theorem is true or not. Most probably it is true because, like I said earlier, if you make an infinitely sized table, then when one column has an x on it, the other column is also going to have an x on it. And I say that to you without constructing the table myself, but I guarantee you if you pick any number, it's always going to work. This pattern is always going to hold. But we can't use the table argument. We have to use a different argument. And actually, I'm just going to save that for a different video. My point here is, this is an introduction. We are just going to, so basically what we're doing, at least for the first part, before we delve into the deeper and more mathy kind of stuff, is to explain why things are right and why things are wrong. Like, for example, over here, we took a statement that is correct and we modified it slightly, and somewhere along the line, something went wrong and we don't really know why or what, and we can't really explain. And basically, this stuff comes up a lot in math, alright? Let's say we have a statement that is true in math, right? Like 5 is less than 6. This is a true statement, but let's try to modify it slightly, by multiplying both sides with -1. That seems like a reasonable thing to do. But what do we have over here? -5 is less than -6. Well, that's not true because -6 is the one that should be less than 5. So we went from a true statement to a false statement by just performing a seemingly innocent modification. But somewhere along the line, something went wrong. Obviously, there are valid modifications that you can make, such as adding both sides by 1, which results in 6 is less than 7. Now that's a valid modification. But again, the question is, why are some modifications valid and some modifications invalid? What went wrong here and what went right here? Lots of questions to ask that will be answered in future videos to come, and hopefully there will be future videos. For now, this is just an introduction. I'm just introducing the idea and the basic concepts here, and hopefully this kind of stuff interests you, and if so, stay tuned for future videos. That's gonna be it for now. See you and goodbye.